right, good morning everyone. Thanks for showing up, braving the snowy weather at 9 a.m. There should actually be bonus marks for that because that kind of sucks. But anyway, so today we will be talking about more memory allocation. So this will not take the whole lecture. I'll spend like the last half of it answering any Lab 4 questions and going over stuff. So we can get through this and then go over Lab 4 stuff and or play with the APIs and make sure you actually understand what's going on with Lab 4 and some of the errors that have been going on. But anyways, let's take a brief detour to more memory allocation and what the kernel actually does in terms of allocation strategies. So one of the allocators the kernel actually uses is something called a buddy allocator, and it kind of restricts the problem to try and minimize any external fragmentation. So typically, it just deals with allocation requests of size power of 2. So 2, 4, 8, whatever, 32 up to a page, maybe even higher than that. So what it does is it restricts allocations to be exactly a power of 2 and lets you have a more efficient implementation. And basically what it does is it will split a bigger block into 2 if the request is too small for that. And then when you split a block into 2, well then those 2 smaller blocks are now buddies. So that's why it's called the buddy allocator. So now if you free one of them, you know that it makes kind of merging things easier, because if you get freed and then your buddy's free, you can merge the nodes back together, and then you might be able to recursively do that and create a much larger block. So this is the whole idea behind it, is it essentially restricts the problem, makes them buddies so that we can do fast searching and also fast merging. We can do them logarithmically. So the most basic implementation of a buddy allocator just uses multiple lists. So you restrict the requests to be some fixed sizes. So like they're all going to be powers of 2. So you pick a big N there, that is your largest request size you will be able to make. And then whenever a request comes in, you just round it up to the next power of 2 if it doesn't fit. And then you just check if you have a free block there. And if you don't, you split blocks recursively to get that size. So if we support allocations up to, say, a page, then you would need n+1 free lists. So you need a free list for every power of 2 size. And then when you get a request come in, it will be to the power of something. So you would search the free list until you find a big enough block. So you would search the K list. So if a request comes in that's like 32 bytes, you would check to see if there's a 32-byte block free. Well, if there's not, then I check if there's a 64-byte block free. And then if there was, I would just pick that and then split it into 2 32-byte ones and then fulfill the request. If I don't have a 60 or 32-byte, I might check 64 and then 128, and you would just go up and up until you actually find a free block. So as soon as you find a free block, you recursively divide it until there's a correct size, and this would create buddies all the way down. And then you insert all the buddy blocks you create into the free list. So you would essentially be creating new free blocks of smaller sizes. And then when you deallocate something, well, you know because you made them buddies that you can coalesce them back together if both the buddies are free. And then you could recursively coalesce the blocks if needed, just going up and then trying to create the biggest block you can. So what's that kind of look like? Well, say we have a buddy allocator and it's managing 256 bytes. So that's all of the memory it's managing at the top. So originally it would have been 1 block, but we used it, and in this case, it currently has 2 allocations, one in the red block, one in the blue block. So anything with the black background just means it was split. It's not actually usable. So there would be 0 free blocks of size 256 because it got split into 2. And then there are 228 blocks here that both got split into 2, so we can't use them. And then there is one 64-byte block there, all the way in at the left. That was split into two 32-byte blocks. So one of them is used for the red allocation, and then we have one 32-byte block free in our 32-byte free list. Then for the 64-byte, there's two free blocks, and then there is one use block in blue. So now following this algorithm, if someone requests 28 bytes, what should I do? Yeah.
Just use up that other 32 block.
Yeah, so if I have a 28-byte request, well, buddy allocator has to be a power of 2, so the next power of 2 is 32. So how many bytes am I wasting, essentially? 4, and is that internal or external fragmentation? So that'd be internal because the allocator itself is only dealing with the block size of power of 2, so it's within a block that it's dealing with that you have fragmentation. So in this case, if that 28-byte allocation comes off, well, I would first look for any 32-byte blocks, and in this case, I have free blocks in black, and then split blocks in red, and then allocated blocks in blue. So if a 28-byte request came in, well, I would check my 32-byte blocks. I have a free one, so I would just use that to satisfy the request. So now I use that 32-byte one, and now I just have two 64-byte ones free. Any questions about that? Fairly good. Oops. Okay, so we just put it in. In this case, I colored it green. So now it's green. So yeah, so now what happens if we have another request come in of size 32? Yeah. Yeah, so I would just pick one of the 64-byte blocks. In this case, I'd probably pick the first one, split it into two, and then, hey, I'm at the correct size now. I have two free blocks, so I'd just go ahead and use one of them. So I split one of the 64-block ones into two. Now I have a purple, I do the purple allocation, now I have a 32-byte block free block. Okay, so trickier question. So what happens if I free that blue 64-byte block now? Yeah.
Would it merge the two 64s and make a free 128?
Yeah, so I free the blue one, and now as part of coalescing and try and make bigger blocks, I would say, hey, my buddy is now free. So I would merge them back together and then have a 128-byte block free, and that's it. I can't merge them because the left side, the buddy of the 128-byte block is currently used, so I can't do anything with that. So any questions about this? Pretty good. And actually a fairly good algorithm to use for memory allocation. So it just restricts it by powers of 2, and it's a lot easier to implement. So it's actually used. It's fast and simple compared to kind of general dynamic memory allocation. It avoids some, but not all, external fragmentation by keeping the free pages all contiguous. But its disadvantages is there's always going to be some internal fragmentation as long as you don't use a power of 2, because you only handle powers of 2. So there is going to be some external fragmentation, if you want to think of it that way. So you could have the scenario where, so say I have a bunch of 32-byte allocations come on, and I split this 64-byte block into two, and then I do all these allocations. So I have 4 32-byte blocks allocated. Well, if I come along and then free them, say I free this one, and then later on I free the one next to it that's not its buddy. Well, in this case, you can't merge them back together because your buddy isn't free. You can't, even though there's like a contiguous 64-block byte there, they're not buddies of each other, so you can't merge them back together. If you did, the implementation would be like insanely, insanely tricky to get right. So this you could think of as being some external fragmentation because you have a 64-byte block free. Say if that was all your memory there, you'd have a 64-byte block free, or not block. You'd have 64 bytes free, but you wouldn't be able to do a 64-byte request. Okay. So the other one that's used is called a slab allocator. And basically all it does is take advantage of fixed size allocation. So every allocation is the exact same size. And we also know that if we have every allocation the same size, there's going to be no external fragmentation because you're just essentially dealing with slots of the same size. So if one's free and another request comes in, you can just refill it. They're all the same size, so it doesn't matter. So, and this, you could have multiple instances of these throughout your program. So like for instance, the kernel uses a lot of things called an inode that we'll see when we do with file systems, and they're all 128 bytes. So because it allocates like millions of these things, so every one of your files and directories has one of these, and we'll see that. It just creates essentially a giant pool of inode of memory that it uses for inodes, and they're all the same size, so it doesn't have to do that much bookkeeping. So every object has its own pool. There's no internal fragmentation. There's no external fragmentation. Everything is good. Everything is the same size. So how you actually implement this is each allocation size just has a corresponding slab of slots, and one slot holds one allocation. So if all your objects or structures are 128 bytes, each slot would be 128 bytes. So what you can do is instead of a linked list keeping track of things that are free, you can just use a bitmap. So there'd be a mapping between a bit and a slot, and you just have 0 means it's free, 1 means it's occupied. So so every single slot would just have a bit associated with it. So bit 0 would be slot 0, bit 1 would be slot 1, bit 1000 would be slot 1000. And then it's really easy to see. If it's occupied or free, and to search for a free element, you just can iterate through it and then find if there's a 0 there. And if there's a 0, you can just return the memory associated with the slot and then set that slot to 1. And then for deallocations, you can just clear the bit to 0, and then you could just be lazy and not reset the memory to 0 if you don't want, because writing the memory is slow. Yeah.
How does the bitmap actually implement it in like MSC language? Do we have such stuff?
So the question is, how is a bitmap actually implemented? So just be like, so everything's byte addressable, so you just have a bunch of bytes, and then you'd be able to figure out which slot corresponds to what bit. But you'd have to do some like bit arithmetic. But when we get to file systems, this is exactly what they use. They use bitmaps to keep track of things. So we'll actually see how it's implemented. You will probably, that lab got cut, so you won't actually do it, but we might show some of it because it's actually fairly interesting. So also, in addition, your slab can be implemented on top of a buddy allocator. So if I'm the kernel, I could use a buddy allocator to do all the kind of more generic requests, and then I could just say, hey, I know I'm going to use a lot of one certain type of object, so I'll just request a big block of memory from the buddy allocator and then implement a slab on top of it and use that memory for a slab. So that would look something like this. So in this example, the buddy allocator would give us memory for each of these slabs, so they're bigger blocks. In this case, say they're like 64 bytes or something like that. And then within each of those blocks given by the buddy allocator, I could use one for a slab for objects of size A, which in this case are small, and I can fit about 4 of them on a block that's the power of 2. So I would have 2 slab A's, for example. In this case, maybe the blocks I'm using for slab B actually fit, and then I don't have any internal fragmentation with those ones. While in my A's, they don't quite fit, so I might actually have some internal fragmentation because I'm using a buddy allocator on top of it. So in this case too, you might be able to be a bit smarter. So if I'm using a buddy allocator, instead of having two slabs for objects of A, maybe I just request a bigger one, and then I could fit maybe 9 instead of 8 on it and use space a little more efficiently, but that comes at some trade-off. All right, any questions about those? And otherwise, we'll dive into Lab 4 stuff. All right, cool. So we saw that kernel restricts the problem for better memory allocation. Buddy allocator is one you'll see forever. If you look actually in the kernel and how it implements memory allocations, it's the buddy allocator. And some user space ones could use the same idea as well. And then there's a slab allocator that takes advantage of fixed size objects to reduce fragmentation. And that's something if you get into like super high performance, if you want your code to be really, really performant and you allocate objects all of the same size, you could use that technique in your own program. So you could just request a giant block of memory and essentially implement a slab on top of it. Okay, so let's go to some examples then. All right, any questions about Lab 4? Yeah.
This is not like an actual code question, but just when you're testing your code.
Uh-huh.
So when I run the command make all test on my code, like some of the tests pass, but then when I run the ECE 344 tester, 0 tests pass, and then when I try to run make all test again, it says like I can't run the command, there's an error. So I have to build the directory every time. So I don't know if that's like a problem with my code or.
No, that shouldn't be a problem with your code. If your build directory, if it doesn't clean your build directory, it's like some weird permission issues on those machines.
Okay, so
Because
is it fine if I just keep testing with make all test and then just submit
yeah,
and try running more?
yeah, it should be fine. So if you look at the code, all it does is remove the build directory, create a new one, do that cmake command, and then make all test itself.
Okay.
So it will do the same thing. But for some reason, for some random students, that it doesn't delete the whole directory. Like the testing directory is still there for some reason. I don't know. It's weird. All right. Any other Lab 4 stuff or weird stuff about Lab 4 we've seen? So there is, oh,
What does it mean, like in the final, in the last tester, what does it mean? There's extra data in the pipe.
so the last test, there's extra data in the pipe, means that the pipe, so it's like the last test. So the last test does this. So if I type test and hit enter, I should only see test come out of it with a new line. And if there's extra data in the pipe, it means it read more than that. So that's all that means. So yeah, if you have read-write commands in it, you shouldn't. You can also mess up file descriptors or have things, yeah, if you connect two processes together, you might have something weird. Basically, you messed up your file descriptors or you wrote something to them. Yeah, and one thing that's like kind of underspecified is, so in this case, if you have some assert, so say in this case, let's see my code. So in some example, I just made, I create a pipe and then I fork, so both processes have all the file descriptors open. Then in the child, I just run cat, and then in the parent, I would just kill it. So if I just kill it, well, it's going to exit, but if I have an assert if exited, then bad things are going to happen. So if I run that, then the assert's obviously going to trip because I just killed it with a signal. So in one of the tests, it's slightly underspecified where if you do things properly, one of your processes will get killed with a signal and you may not be handling it correctly. So how that would happen, let's see. Yeah, so let's see, dupe2. Fg's 1. So say I have this. So cat would write out to the pipe, and then in this case, the parent's the only reader of the pipe, so nothing would happen. So if I just run it, oh, right, I still kill it. So if I do this, nothing's going to happen. It's just going to sit here and wait forever because it writes things to the pipe and nothing's there to read it. And nothing will cause cat to finish. So it's connected to standard output. If I did that, that input is actually being read by cat. It writes it to the pipe and nothing reads that pipe, so it's kind of useless. So what you might see as an error if the parent goes ahead and closes FD's So the parent, so the child here is writing to a pipe, and then the parent just closes all the file descriptors, and all the file descriptors in the child are closed to all the extra ones. So so for bonus points, what will happen if I type in hi here and then I hit enter? Sorry? Pipe failed with descriptor error. So the kernel is actually quite smart. So what is going on here is there are two ways to exit a process. There's if exited, so clearly if exited isn't true. So we could do something if exited is true. But the other case, how else could a process end? Well, it could end with a signal. So we could check if it got killed by a signal. So fprintf. So if I do that, a signal got me good. So my child got killed by a signal. That's weird. So if I look at the wait documentation, I can see, well, there's if signal returns true if that process was terminated by a signal. So it was terminated by a signal. And then it says, oh, I can use wterm sig returns the number of the signal that the child process to terminate. This macro should only be employed if signal is true. Well, it's true. So let's just print out what it is. Oops. So signal 13 got me. So was it man signal? Wonder if it says. Oh God. Okay. Okay. Anyways, I'll just let you know, signal 13 is a pipe signal. So the pipe signal means that the kernel is smart. So in this case, there's one process that can write to a pipe, and then all the read ends are closed in both processes. So the kernel is smart enough to know that whatever it writes to the pipe is never going to be read by anything because nothing right now has a file descriptor open to the read end of the pipe. So the kernel is just going to be smart and be like, yeah, well, nothing can actually read any data you write to this, so I'm not going to let you write data anymore, and it just kills the process. Because otherwise, why would you write data to it that nothing can possibly read? So this is like the underspecified part that I posted on the Discord. Because one of your test cases is something like, what was it? You name cat true. So because of this, if everything is working correctly, well, I have a pipe between cat and true. So there's the right end of this pipe connected to the read end of this pipe. And that should be, this should be the only process that has a file descriptor open to the right end of the pipe. And this process should be the only process that has a file descriptor open to the read end of the pipe, and this one to the right end of the pipe. So because you launch all of these and you have no idea which one exits first, well, true doesn't read anything from standard in. It doesn't care. It just exits with 0. And then this could exit before cat, and it would close the read end of the pipe and then this cat would get a signal that would get that signal pipe signal. If that makes sense. All right. Any other Lab 4 questions? Wow, we have a lot of time. Or other fun stuff. So, another fun question I saw was, here, let's get rid of it, was about the first argument, like, of this exec VE. So it might be weird. Anyone know why this thing's duplicated, why there's 2 cats? Yeah.
It's not just standard that you have to have the command as the first read.
Yeah, so this is the program to run, and then this is all the command line arguments. That would be argv, and this is just a convention because anyone want to tell me what would happen if I did this? So I got it does not exist here. So it's going to so if I do that, it doesn't get do not exist. It kind of works. It should just be doing cat stuff. So it's all fine. So it's just a convention. So this is the name of the program to execute. So if I did haha here, okay, what's going to happen now? Actually, I don't. So if I do this, what's going to happen now? Huh? It's all over. So if I do this, haha doesn't actually exist. So the first one is definitely the name of a program, and the other one doesn't seem to matter. So the other one only matters because if I write out main would usually look like, main usually looks like that. So this argv thing is set from execve. So if for some reason I read argv0, that's essentially what this argument is. And no one essentially reads from it except, which makes this kind of funny. So I could do cat. Cat by default is kind of what it should be. So let's make cat do something. So usually the only thing that reads arg0 is a help message. So if I do that, that's fine, and run this, well, you'd get the help message, right? That's all usage cat, option file, everything like that. Well, if I go ahead and change cat to haha, The convention is that's what you type to actually run the command. So it should probably match stuff. So if I do that and I do the help message, instead of cat, it says haha. Just to print you out, and it's only a convention to give you better print messages, because the expectation is I typed haha, and that's how I ran this command. So all of it says haha, even at the top, usage, haha. So yeah, it essentially, and all it does is set this argv thing. So argv, no one's probably ever looked at argv0 ever in their program, but it's set, and usually it's just used in help messages by convention. All right, any other Lab 4 stuff or anything at all? Yeah.
With regards to election, not before.
Uh-huh.
You said the buddy allocator is used like actually in practice, right?
Mm-hmm.
So is that why you always try, like if I were to allocate like 49, 7 points, that would be like really bad.
Yeah, but malloc doesn't generally use it. So malloc uses like, depending on the implementation, we'd probably use like the first fit or best fit thing, like the really general one.
But the kernel does it that way.
Yeah, the kernel would do that, because if you're the kernel, the only one allocating memory is yourself, so you wouldn't do anything that silly. So the kernel developers are actually pretty good, so they wouldn't do 1 byte over the limit and make it waste a bunch of memory. But yeah, so that's why they use it, because it's restricted, but if you're the kernel, you're allocating your own memory, so you can be careful about it. But there's a bunch of, if you really care about performance, there's a bunch of, you can replace malloc with a bunch of different ones. So for example, Chrome, I believe they use something called JE malloc, which is a different malloc implementation with different trade-offs, mostly that it's faster, but might waste some more space. But Chrome likes wasting space anyways, so they'll take the performance bump. Yeah.
So that's why you said malloc might not use something like that, but is that why you said like for performance you can use malloc to get like a really big block of memory and then use your own like slab allocator, buddy allocator with that?
Yeah, you could do that. Also, another option you have is there's a system call, you can just get virtual memory from the kernel. You can just say, hey, give me some pages, and then you can deal with them however you want. But in general, there's only one thing that manages the heap, and that should be the malloc call. But if you want to request different memory from the kernel, you're free to. Yeah.
Can I change the page size of the kernel?
So question, can I change the page size of the kernel? And the answer to that is it depends on what architecture you have and what kernel you have. So that's actually a good question. So let's go here. So who remembers, so when we had SV39, that had a 39-bit virtual address, it kind of looked like this. There was 9 bits for my L2, 9 bits for my L1, 9 bits for my L0, and then there is a 12-bit offset. So if I'm following this, typically your hardware will still have a set page size. That's still going to be 4 kilobytes. But if you wanted to, the next natural size to use, if you wanted to do a bigger page size, is, well, I would just get rid of a level of page table. So I'll just get rid of this level and then increase my page size, which would increase my offset bits. So instead of 12, now I have 12 plus 9. So 12 plus 9 would be 21. And then this would be an L1 and then an L0. So if this is how many bits I use at my offset, what page size is this? If people are good at powers of 2. So 2 to the power 10 is 1 kilobyte. 2 to the power of 20 is a megabyte. Yeah,
2 megabytes?
yeah, 2 megabytes. So at least in the Linux kernel, you can use 2 megabyte pages. Any recent-ish architecture will support that, and some programs actually really want to use 2 megabyte pages because your TLB coverage gets better too because there's less things to translate. So instead of translating 27 bits, I'm translating 19 bits instead. So, and because my page sizes are 2 megabytes, well, if I do one translation, it covers 2 megabytes instead of 4 kilobytes. So it will be faster on most of them. There's like some kind of push now that's like, hey, we have so much memory now, things may as well be 2 megabyte pages. But that's still not super frequently used. But some programs actually like this, and you can, there's like, if you get really interested in this stuff, there's like blog posts about that. You can go read blog posts of programs that like 2 megabyte pages. But then, as you can see here, well, I could be a little bit smarter and be like, yeah, screw this multi-level page table. If I remove another level and I just have one level of page table, how big are my pages going to be? Yeah, so there'd be 1 gigabyte pages. So those are, what do they call them? So I think the 2 megabyte ones are called huge pages. I don't know what the gigabyte ones are called, but you can use the gigabyte pages, but if you want, and generally all your TLB entries will be hits because, yeah, because you have a lot of TLB slots and they each cover a gigabyte.
So the number of bits in with offset is like the size of the page, right?
Yeah, the number of bits in the offset is however many bytes you can reference in the page. So it's essentially 2 to the power of that is the page size. All right. Any other questions so far? Are we lab 4? Everyone's done lab 4-ish? Everyone's done lab 4-ish? Okay, well, in that case, I'll hang around if you have any lab 4 questions. I can read something since we have extra time. It's getting to that point of the course where we're running out of content, and I think we're slightly ahead of the other ones. So just remember, pulling for you. We're all in this together. Oh.